So before we get started with the new content for today, which is day 4, there were a couple questions sent to me before lecture that I wanted to talk about. Just as a reminder, I do have the lecture text channel open on my phone, so if you do message me there, I should be able to see that throughout the lecture. You can always unmute yourself and just ask a question verbally too. That's always a good idea to interrupt me and make sure that I don't overlook the questions that you have. So I believe the specific parts of this question that were requested to be covered were B and D, and it makes sense that you would have a question about these because when we look at the compounds here in B, for example, they're both nonpolar, so the only type of intermolecular forces they can have with identical neighboring molecules are London forces, right? The electrons would have to randomly shift to one side, creating maybe a negative side and a positive side, and then another one of those molecules, for a 6-membered ring, the electrons would shift and create temporary partial charges to attract. So if the only type of attraction between two 6-membered rings is London forces, and the only type of attraction between two 5-membered rings is London forces, well, how do I judge which one has a higher boiling point? Well, I have to look at either how strong the London forces will be or how many instances of partial charge formation can occur around the surface of that structure. So the strength of the London forces mainly has to do with the number of layers of electrons, because as we were saying, we talked about this, if I have an element with multiple layers of electrons, the outer layers are shielded from their attraction to the core by the inner layers of electrons. The repulsions between all these layers of electrons push the outer electrons far out, and they can slosh around and create much larger temporary quantities of partial charge. In the case of these two molecules, though, carbon has its outer electrons in the second energy level, and that's the same for both molecules, so the degree to which the electrons can shift around here is about the same. The strength of the intermolecular forces between these two 6-membered rings and two 5-membered rings are going to be about the same because there's the same number of layers of electrons here as there is here for the most part. So then the second factor that determines how strong or overall how strong the London forces are going to be, so really I shouldn't say strength here because both of these affect strength. I should say the quantity of charge. There will be larger quantities of partial charge if I have more layers of electrons to slosh around. So the second factor is going to be the surface area. And that's the key factor that allows you to answer both B and D, as we'll see. So here, if the ring is smaller, there's not as much surface area as there is in a larger ring. And when the structure is larger, there's just more electrons total, more surface area in the structure, more opportunity for small parts of the electron cloud to temporarily shift to one side and create a larger number of potential partial positives and partial negatives all over the surface of the structure. If the surface area is more minimal, there's not as much surface area, then it's less likely that those small shifts of electrons will create very many partial positives and negatives around the surface. So it's not just about thinking how strongly can two of these structures attract. It's more about thinking if I got one of these molecules and it's surrounded by a whole bunch of them, the boiling point is going to be determined by how much energy does it take to separate all of these from one another. And if I have a more surface area and a larger number of temporary partial charges that form around the surface, then you can potentially form attractions with the greater number of neighbors, and it's going to take more energy to break all those and force something from the liquid state where the molecules are close together to the gas state where they're farther apart. And so we use the same logic here. So in this structure here, because of the OH and the polarity associated with these OH and OC bonds, so here I've got some temporary dipoles, some fairly large partial positives on the carbon and hydrogen, same thing here. And a large partial negative on the oxygen. So this molecule can hydrogen bond to a neighboring structure. I'm just using the bond line representation here. It's much easier to draw, much faster. So the partial negative, partial positive there attracts. So both of these molecules can form hydrogen bonds between each other. So one molecule of this type and another molecule of the same type can form hydrogen bonds. Same thing here. 4-carbon chain. 1, 2, 3, 4. Fourth carbon's bonded to an OH. The oxygen can attract to the hydrogen, partial negative, partial positive. This oxygen can attract to this hydrogen, partial negative, partial positive. So hydrogen bonds are going to exist in both instances. The difference is this branched carbon structure is more compact and spherical versus this more extended chain structure is got more surface area. So with more surface area, there's just more opportunities for the electron clouds in small areas around that surface to temporarily shift in one direction or the other and create tiny areas of partial positive and negative so the molecule can attract neighboring molecules. When the surface area is more compact, you're just not going to get as many temporary partial positives and negatives around the outside. So the difference between the boiling point of this terbutanol versus standard butanol or normal butanol has to do with the surface area and the London forces that result from the attractions that occur in the nonpolar regions, because as far as the polar regions are concerned, they're both capable of fairly strong, similarly strong hydrogen bonding, and that won't differentiate between them. Any questions about that? Alright, so then there was a question about this one from the textbook. Specifically, was requested to take a look at E, so we'll do E, maybe one other one. If anyone has any preference, feel free to message your preference of which one of these you'd like to see worked out. But if we're trying to draw a Lewis structure, I would also, at this point on the exam this week, probably also ask you to draw a bond line structure, so we could do both of those. But when drawing a Lewis structure, the condensed structural formula, we have to interpret this in a way that completes all the noble gas configurations and gives all the atoms octets, and so that's really where students get tripped up sometimes. So this end carbon here, I might not even show this double bond. You have to understand that even if that's not shown, if I just drew CH2 and then CH and didn't show the double bond between them, etc., well, if I'm drawing this as a Lewis structure and I only have 2 hydrogens on that carbon on the end, and the next carbon only has 1, and the next carbon over has 2, etc., well then that's not enough electrons to complete the noble gas configuration, so it would be assumed, or you would have to assume, that there's another pair of electrons in here to complete both of those octets. So it's also a really good idea when you're working on these to number them so you don't lose track of any carbons. It's really easy to lose track, so I like to do that myself. 1, 2, 3, 4 carbon, 5, and then here I've got 2 of these CH3 groups, right? This thing in parentheses, I've got 2 of those, so that would be 6 and 7. Right? So far we've drawn carbon 1, 2, and 3, and the way I'm interpreting this is I'm looking at carbon 3. It's got 2 hydrogens, and I can assume it's bonded to the next element in the line here, which is an oxygen. So I would put an oxygen there. And then that oxygen looks like it's bonded to carbon 4, which has 2 hydrogens. I know that, obviously, because there's 2 shown right next to it. The oxygen would need 2 lone pairs to complete its noble gas configuration, so that's got to be assumed as well. And then, so this is carbon 4. Carbon 4 is bonded to carbon 5, which only has 1 hydrogen. And that means it needs 2 more bonds to make its noble gas configuration, and that's why there are 2 CH3 groups. So I would draw one of them in here. Oops. I probably would want to actually show the hydrogens if I'm asked to draw a Lewis structure and show all the bonds. And the other CH3 group there. And then if I want to draw the bond line representation, I would have carbon 1 bonded to carbon 2, 2 be bonded to 3, 3 be bonded to an oxygen, the oxygen be bonded to carbon 4, 4 be bonded to 5, and then 5 is bonded to 6. Oops. 6 and 7. Any questions about that?
I have a quick question.
Sure.
So, what threw me off when I did this is my structure looks similar to yours, and when I checked the solutions guide, their branching was just placed differently.
Oh.
So does it matter where it's placed?
So later when we get further into the textbook, we'll see that sometimes the direction and space that a bond is angled at or pointed in does matter, but sometimes it doesn't. So we have to get into an in-depth discussion about that later. And so for the time being, you don't have to worry about that at all.
Okay, thank you.
So wherever I show these in space, and I could have put this, well, typically when we draw the bond line structure, we want to spread everything out. So I would still put that bond there and the other bond here. But in the Lewis structure, I could put the CH group over here and move the hydrogen over there. As long as I have all the right connections, it doesn't really matter where they're pointing in space as far as we're concerned at the moment. Maybe I'll just pick J. We'll just do one more real quick. So here I've got this stuff in parentheses shown first. Typically when I have something shown in parentheses, though, that means it's kind of hanging off as a side group. So I might label this carbon 1 to begin with, and that carbon has a hydrogen and an OH, and as we just said, it doesn't really matter where in space around the carbon I draw those. And so that means it needs 2 more bonds, and that's why I've got 2 of these things in parentheses. So each one of these is a CH2, CH2, CH3. So I've got 2 of those. So here's 1. Oh, actually, I'm trying to draw the hydrogens out here. 1, 2, 3. CH2, CH2, CH3. So that's one of those groups attached to this carbon. And since I've got 2 here, it shows I've got 2 of them, so that I can draw the other one down here. Again, it doesn't really matter at the moment where I draw them in space. And so that would be a good way to draw that Lewis structure. Notice that when you draw the Lewis structure, it's kind of easy to get into this habit of making the angles look like 90 degrees, or the angle between this bond and this bond looks like 180 degrees. Now we know those aren't the angles. We know they're close to 109 when it's sp3 hybridized and the steric number is 4. And so that's one advantage that the bond line representation has. So if I were to draw this as a bond line representation, I'll count the carbons from left to right. 1, 2, 3, 4, 5, 6, 7. So now I would just draw that zigzag. 1, 2, 3, 4, 5, 6, 7 to represent those 7 carbons. I've got the OH group on carbon 4, so I just show that coming off at an angle. And now very quickly I'm able to draw a structure that looks much more similar to what the structure should actually look like in 3 dimensions. So also my intention is this week, and for those of you who have lab on Monday, it would be next week, to assign to each of you a model kit that you can take home and work with, because looking at these things in 3 dimensions on only using a 2-dimensional screen is really challenging to do. So especially now and moving forward in the next couple weeks, ideally you'll want to work with your model kit often and try to make three-dimensional structures of these so you can start to develop mental images in 3 dimensions that match the 2-dimensional screen and be able to work back and forth. So working with the model kit is a good way to help you translate from one type of representation to thinking about what the structure really looks like 3-dimensionally. Any other questions about anything? Alright, so continuing then where we left off last week, we were talking about bond line structures and some of the advantages that they have over other representations. As I was saying a moment ago, these condensed structural formulas are one of the worst ways to show a structure. They're nice in that they show which atoms are connected to which atoms. So I know that this carbon has 3 hydrogens, this carbon has 1 hydrogen, etc. But they have a number of flaws. One is it's kind of hard. You have to go through atom by atom and kind of interpret the structure and draw it out. The bond line representation is superior to that. But one other advantage of the bond line structure is it's very easy to quickly hone in on where a site of reactivity might be in the molecule. So double bonds and triple bonds are typically much more likely to undergo certain chemical reactions we'll talk about later in the semester than single bonds. And so we want to make sure we can quickly identify those, and since there's not a bunch of hydrogens and carbons shown everywhere, it's very easy to see that double bond and to recognize what's happening in this reaction. The double bond turns into a single bond. So what's tricky about this, and I definitely recommend in the beginning when you're working with bond line structures and you're trying to use them to interpret reactions, or soon we'll be talking about acid-base reactions or in like resonance structures, it's really a good idea for now to draw in any hydrogens that are present. Because if you don't, it's easy to lose track of how many hydrogens there are around sites where reactions are occurring, right? So on this carbon here, there's only 1 hydrogen because it already has 3 other bonds shown. On this carbon here, there aren't any hydrogens because there are already 4 bonds shown. So between those 2 carbons, in the beginning, there's only 1 hydrogen. Later, after the reaction occurs, now this carbon here only has 2 bonds shown, so it has to have 2 hydrogens attached. And this carbon here has 3 bonds shown, so it needs a hydrogen attached. Right? So it's not a bad idea to draw the hydrogens in, especially in an area where a reaction might be occurring. That really helps you to see the change that's occurring on the structure. So we can easily tell that this hydrogen maybe was already here, but we had to add 2 more hydrogens, and that's the purpose of the H2 molecule. It supplies the hydrogen atoms that are needed to add across that double bond and create new sigma bonds, new CH sigma bonds. So you definitely want to get used to working with bond line structures. We're going to be working with those almost exclusively moving forward, and they have a lot of advantages. The one disadvantage is, as I said, the hydrogens aren't shown. So in the beginning, I recommend you draw them in so you don't lose track of them and accidentally draw a 5-bonded carbon or overlook hydrogens that are there and thinking they're not there when they really are or something. Another advantage of bond line structures is you can quickly see other sites of reactivity, and we call these sites of reactivity functional groups. So they're either individual atoms or often groups of atoms. We call them functional because they undergo reactions. So each grouping of atoms is a functional, it has a function, or it has a set of reactions, chemical reactions that it will be likely to undergo. So if I have a halide, which is chlorine, bromine, or iodine, technically fluorine is also a halide, but fluorine isn't very reactive. So if I have fluorine bonded to a carbon, usually not much will happen there. So we don't usually work with chemicals that have fluorine present. Chlorine, bromine, or iodine, if chlorine, bromine, or iodine bonds to a carbon, there's a set of reactions that typically will undergo. We'll talk about that later in the semester. So anytime you have a non-carbon atom, it's got to be shown in the bond line representation, and the advantage of that is it draws our eyes to it, and we can quickly start to imagine the types of reactions this molecule might undergo once we get into discussing those reactions. Double bonds and triple bonds, as we said, are somewhat reactive. Double bonds undergo a certain set or series of reactions, which we're going to learn about. And so drawing those in your bond line structure draws your eyes to that and allows you to think about the reactions they might undergo. Same thing with triple bonds. So double bonds are called alkenes. Triple bonds are called alkynes. And the terminology we'll be using, so hopefully you'll get used to it as we discuss that. And we're going to talk about these functional groups as we go, a little bit at a time throughout the semester. So you don't have to worry about them all right now. You don't have to memorize them. All of these functional groups are on your formula sheet. So, if I say compare the boiling point of alcohol with ether like that, you could use a formula sheet to look up, okay, alcohols have an OH group. That means there's a big electronegativity difference here, and the large partial charges set this up to hydrogen bond with neighboring molecules. So that should probably have a higher boiling point than a typical ether, because in an ether, there's only a minor dipole to attract neighboring molecules versus the large partial charges that form because of the especially large electronegativity difference between oxygen and hydrogen. So there are thiols, aromatic compounds. We'll talk more about those in organic chemistry too, as well as thiols. Ketones and aldehydes involve a CO double bond. Soda carboxylic acids, we're going to talk about carboxylic acids soon. These are acidic, you might remember from general chemistry, because of their likelihood of losing an H plus and keeping the electrons behind on the oxygen. That's stabilized through resonance, which we'll talk about here in a minute. So that's what makes those acidic. And you should also start to recognize that the letter R is the most commonly used letter just to represent a generic grouping of carbons. So R is typically one carbon and as many hydrogens as it needs to make its noble gas configuration, 2 carbons, could be 3 carbons, could be 4 carbons. R could generally represent any number of carbons. They could be an extended chain, they could be branched, I could put any other carbons I want, I could put a ring here, whatever. If it's just a grouping of carbons, it's often going to be designated with the letter R, and that's used especially when I've got a large group and I don't want to have to take the time to draw the whole thing. If I know that group's not involved in any reaction or in change of any kind, I'll just represent it with the letter R so I don't have to keep drawing it over and over again. It's just kind of a shorthand.
Do you want us to memorize these functional groups?
No, I wouldn't worry about it. They're on the formula sheet. You'll have that all semester, so there really isn't any need to memorize them. And as we go through them individually and start talking about them in detail and use their terminology over and over again, it should kind of start to become second nature without the need to actually sit down and memorize them.
Thanks.
Sure. All right, so when you see a bond line structure, if the lone pairs are shown, which they should be, you should be able to calculate the formal charge for any atoms that have formal charge. So that's a skill that I might ask you about. So we're still applying the formal charge formula. The only difference is we're not showing the carbons and we're not showing the hydrogens that are bonded to the carbons. But it's still the same thing. So for example, this oxygen, it's in column 6A on the periodic table. So for oxygen, it would normally need 6 valence electrons to be neutral or balanced in charge. Right? It needs 8 for its noble gas configuration. But when we're looking at formal charge, we're not concerned with that, right? We've got 2, 4, 6, 8 for its noble gas configuration. That's good. That makes it stable. But to be optimally stable, it should have 8 or an octet around it total, but also only assign the number it needs to be balanced in charge. And so you got to remember that any shared pair counts toward both atoms' octet or noble gas configuration, but when I have a shared pair, only one electron can count toward each atom's charge. So the oxygen has 2 electrons to itself, and it has 2, 4, 6 that it's sharing, and only half of those will count toward its charge. charge. So that's 6 minus 5, or plus 1. So what that means is it was sharing too many. It didn't have enough all to itself. It needs 6, but it only had 5 around it, so there's a net plus because it doesn't have as many negatively charged electrons around it as it normally need to be balanced in charge. And so you would just want to label that charge there. And then you'd want to do that for all the atoms to get used to the formula. But once you calculate for an atom its charge when it has a certain number of bonds and a certain number of lone pairs, if you see the same atom somewhere else, so let's say I had an oxygen with 3 single bonds and a lone pair, well, that would have the same charge as an oxygen with a single, a double, and a lone pair, because it's still the same number of shared electrons, 6 shared electrons, and 1 pair all to itself. And so you can start to recognize patterns there, and anytime you see an instance where an atom has a certain number of bonds and lone pairs, if the same atom, or even another atom in the same column, has the same number of bonds and lone pairs, it'll always have the same charge. So this oxygen here, it needs 6 valence electrons to be balanced in charge, but it has 2, 4, 6 all to itself just from its lone pairs, plus 1 more from the pair it's sharing, and so that gives it a negative charge. You always want to label that on there. So anytime an atom has a formal charge, always label it. And then this nitrogen here is the other one where you'd actually end up with a formal charge. Nitrogen is in column 5A, so normally we need 5 to be balanced in charge. It doesn't have any all to itself because it doesn't have any lone pairs, but it has 2, 4, 6, 8 that it's sharing, and only half of those 8 actually help to balance its charge, and so that gives it a plus 1. And you'd want to label that on there. We could talk about the quiz question where you're meant to calculate charges. So there are 4 of them on here. This oxygen is very similar to the first one we looked at on the last slide, where the oxygen has 3 bonds. So instead of showing these here, if it's easier, you can actually show them bonded. So here the oxygen has 1, 2, 3 bonds and a lone pair. So for that's going to be 6 minus the 2 it has all to itself, and half of the 6 it's sharing, and so that gives me a plus 1. So label that there next to the oxygen. This nitrogen here has a charge. Nitrogen needs 5 to be balanced, but it's got 2, 4 all to itself, and half of these 2, 4 that it's sharing, and so that gives me 5 minus 6, that gives me a negative 1. Sometimes students overlook sites that look stable because they have noble gas configuration. So this phosphorus, if we were to draw out the hydrogens, has 4 bonds. It looks relatively stable. But phosphorus is in the same column as nitrogen. It needs 5 electrons to be balanced. So it's stable in that it has an octet, but we also always want to look at that as well as the charge. And in this case, it has 8 electrons shared, no electrons owned completely by itself. And so that's 5 minus 4. That gives you a plus 1. And then the other one sometimes students overlook is carbon. So typically carbon doesn't have any charge. Any carbon, to really be stable, will need 4 bonds to make its noble gas configuration. And when it forms 4 bonds, since it's in column 4A, that gives it just enough electrons, half of the 8 it's sharing, count toward balancing its charge, and so that's perfect for carbon. So when you have a carbon in a bond line structure, it won't be labeled, and the hydrogens present also won't be shown, but you should assume that it makes a noble gas configuration unless it has a positive charge. So unless the charge is shown as positive, it's going to have a noble gas configuration. And that means in addition to the 1, 2, 3, 4, 5, 6 electrons that are shown there, it needs a hydrogen that is not shown. So you should be able to interpret this carbon as having 1 hydrogen. That gives it the 4 pairs it needs to make its octet or noble gas configuration. And so when we calculate its formal charge there, since it has a lone pair, 2 electrons all to itself, and now it's sharing 1, 2, 3, 4, 5, 6 electrons, That gives me 4 minus 5, or negative 1. And so that ends up producing a formal charge on that carbon of negative 1. And so when you're dealing with carbon, there are really pretty much only three ways you'll ever see it. Typically, most of the time, it'll have 4 covalent bonds because that allows it to have both an octet and avoid carrying an unstable formal charge. We just saw an example where it was negative. That will occur. It's pretty unstable. We'll talk about why that is in a minute. And sometimes you'll see it with a positive. So if I show carbon with 3 bonds shown in a positive, or 2 bonds shown in a positive, or 1 bond shown in a positive, that is called a carbocation, right? Cations have a positive charge, so it's a carbocation if it's a carbon with a positive charge. So is it correct then to say that this carbon has 3 bonds, this carbon has 2 bonds, and this carbon has 1 bond? No. All 3 instances, the carbon has 3 bonds, right? So if you see a positively charged carbon, that means it has 3 bonds. Why is that? Well, it's the way the formal charge formula works out, because carbon needs electrons to be balanced. And so the number it would have to have assigned to it to end up with a plus 1 formal charge would have to be 3. Right? So if I solve this algebraically for x ends up being 3. That's how I get a plus 1 if I subtract a number from 4. So the way I end up with 3 electrons assigned for a positive charge is if it has 3 bonds, because that's 6 total electrons, but only half of them would be assigned to the carbon since they're shared with other atoms. And that gives me 3 electrons assigned, so I subtract that from the 4, it needs to be balanced. That's how I get the positive, the plus 1 charge on it. So if there's only 2 bonds shown, I have to interpret that and understand that the 3rd bond is to a hydrogen. If there's only 1 bond shown, I have to interpret that and understand that the other 2 bonds are to hydrogen. And so as I was saying, when you're using the bond line structures, for now, it's probably a good idea to show the hydrogens. That way, if you're moving electrons around, you don't accidentally move too many electrons onto a carbon. You can't ever have more than 8 electrons, no matter what. But this isn't a very common way to see carbon with a positive charge. As we said, it's almost always neutral. If it does form this way, it won't last for very long. It's very reactive. Why is it reactive? Well, there are really 2 reasons. One, because it has a net positive. That's pretty obvious based on the formal charge. And that's unstable because it's going to start attracting negative charge in there. But even more importantly, too, I'm going to make this number larger since it's more important, it doesn't have a noble gas configuration. It doesn't have an octet. There's an empty orbital in the 2nd energy level that's pretty close to the carbon's nucleus that would be really good at attracting electrons in there to complete the noble gas configuration. So the way we pretty much always see carbocations reacting or behaving in reactions is any other element that has a pair of electrons that could be shared will come in here and start sharing those electrons to produce that 4th bond, and that will create a new covalent bond where the orbital of this will overlap with the empty orbital of the carbon, which is the orbital, and when that overlap occurs, there's just enough electrons to get into the bonding molecular orbital, and that forms a stable covalent bond. So we almost always see carbocations attacked by molecules with lone pairs to form the 4th bond. But you do want to be aware that carbocations can form temporarily in reaction. We'll see lots of examples of that later. So carbon's almost always neutral. Once in a while it might lose electrons to become positive, in which case it makes it very susceptible to picking up new electrons and forming a new bond. And then the 3rd type of way you might see carbon, there is a 4th, but we don't really cover it. It's more of an advanced organic chemistry topic. So the 3rd most common way we'll see it is as a carbanion. So anion means negative, carbanion means a carbon with a negative. And so what's stable about this is at least it has an octet, right? 2, 4, 6, 8 electrons around it, gives it a noble gas configuration. and it only has one extra negative when we calculate its formal charge. It's only a -1. So why is that unstable? Well, as we were saying before when we first talked about formal charges, we said the smaller the atoms, smaller atoms are especially unstable when they have charges. And that is because of the charge imbalance, or the ratio of positive to negative being unbalanced or not close to a 1-to-1 ratio. Right, so when we look at carbon, it has 6 protons in its nucleus. If I give it a net negative, that means there's 7 electrons total around it. So if I take 7 divided by 6, real quick in my calculator, I get a value of 1.2 roughly. So that means there's about 20% more negative than there is positive. Doesn't maybe seem like much, but it's a fair amount. And the smaller the atom, the fewer the protons are, the more one extra electron affects that balance and makes it less balanced and makes it unstable. So how is a carbanion likely to react? Well, carbanion, since it has too much negative, it's likely to start sharing its electrons with anything that can accept those electrons to form a new bond, like a carbocation. So if I put a carbanion in with a carbocation, what will they do? They're just going to bond together. The carbocation has an empty orbital. The carbanion has a full orbital. When those orbitals overlap, I have just enough electrons to go into the bonding molecular orbital that's created from that overlap, and those electrons can be shared over both atoms to complete both their noble gas configurations and balance out all the formal charge. You have to show the charge in your bond line structure. If I don't show the charge, if I just draw a bond line structure and I don't show the charge, that's confusing. Right, so let's talk about that a little bit. Right, so we just said if there's a lone pair and 3 bonds, it'll be negative. If I don't show the negative charge here, though, someone would assume there is no third bond. It's possible a carbon could have 2 bonds in a lone pair. That would also be neutral. So 2 bonds in a lone pair is still only 2, 4, 6 electrons around that carbon. So it doesn't have a noble gas configuration, so it's pretty unstable. But it doesn't have a formal charge, so it's not like super unstable. That's called a carbene. A carbene is pretty unstable because it doesn't have a noble gas configuration. So if I don't show the charge, someone would assume that there's no hydrogen attached here. So if it is a carbanion rather than a carbene, I have to show the negative charge so that someone understands there's a hydrogen there, because typically the hydrogens won't be shown in a bond line structure. Alternatively, if I have a carbocation, I have to show the positive charge, right? Obviously, if I don't show any charge here, you would assume that there are 2 hydrogens and it's got a noble gas configuration. So if there isn't, and it's actually positive, I have to show the charge there. That's the only way for you to know that there's only 1 hydrogen and that it's missing that 4th bond and that it has the formal charge. So it's critical to communicate about these structures. If there's a lone pair, you always have to show it. If there's a charge, you always have to show it. And so this slide illustrates the same thing. If I have a nitrogen, if I don't show the lone pairs and I don't show the charge, then I definitely don't know the situation that I'm dealing with. Right? So this is really incomplete. It doesn't correctly communicate fully about the situation. So the situation here for nitrogen, if the nitrogen only has 2 bonds, there's a number of ways it could exist. I could have 2 lone pairs, which would be a negative, so I would want to show both the lone pairs and the charge. I could have 1 lone pair, which would be a positive and an incomplete noble gas configuration, so that would be really quite unstable and very unlikely. I could also have something called a free radical, which I always thought was a cool name. A free radical is any instance where I've got a single electron rather than a pair of electrons. Instead of a lone pair, I have a lone electron or a single electron, and that's pretty much always going to be unstable because I'm never going to make an octet or a noble gas configuration if I have an odd number of electrons. So I've got 2, 4, 6, 7. 7 total electrons is not a noble gas configuration. And so that's also going to be unstable. But it's important to draw in all the electrons that are not shared and any charges that exist to be clear when you're communicating about the structure. So I might ask you to draw in lone pairs, and you could use the formal charge formula to figure out how many lone pairs there are on an atom, but I'd have to show you the charge, right? So like in this example here, if I don't give you the lone pairs and don't show the charge, there's no way you can know how many lone pairs or how many electrons would be on that nitrogen. If I give you the electrons, you should be able to calculate the charge. If I give you the charge, you should be able to calculate how many electrons there are using the formal charge formula. So let's look at an example of that, right? So here I've got an oxygen. I might show you the charge and ask you to figure out how many lone pairs there are. That's a legitimate question. So we know that oxygen should have 6 valence electrons because it's in column 6A if it's going to be neutral. So it should have, right, if neutral, it should have 6 valence electrons assigned to it. So if it has a negative, that means I know there's one extra negatively charged electron around it. So instead of having the 6 it would need to be neutral, it needs one additional one to create an extra negative, and so that means it has 7 around it. So if I already have a bond shown, a shared pair, only one electron from that bond actually counts toward the oxygen, the other counts toward balancing the charge of the carbon. So if I only have one shown, how many more must there be in order to get to a total of 7? Well, there need to be 6 or 3 pairs. All right, so here, Y is only one electron assigned to the oxygen from the shared pair, because the other electron is assigned to the carbon. Right? We always split them. We split them to assign them to both atoms. And so here I need 3 pairs. I would have to draw in those 3 pairs. That way it has 6 total by itself plus 1 more from the shared pair. That assigns 7 to it. And when it only needs 6, if it has an extra electron, that's what accounts for the extra negative charge there. So once you work with these atoms enough, you'll start to observe some of these patterns. And if you want to memorize this, you're welcome to. You can also use the formula and the process we just went through, so you don't have to memorize it. But if I have a negatively charged oxygen with a single negative charge, it's always going to have 3 lone pairs and 1 bond. That's how I get to a negative charge using the formal charge formula. If it's a neutral oxygen, it's got to have 2 bonds and 2 lone pairs. There's really no other option. That's how I get 0 formal charge when I use the formal charge formula. It doesn't have to be 2 single bonds and 2 lone pairs. It could be a double bond and 2 lone pairs. But it's got to have 2 bonds and 2 lone pairs. If it's positive, an oxygen is pretty much always going to have 3 bonds and 1 lone pair. It could be a double bond, a single bond, and a lone pair, or 3 single bonds and a lone pair. But 3 total bonds and a lone pair is the format you get that creates a positive charge on an oxygen. And if you do a bunch of examples where you calculate a formal charge, you'll start to see that pattern, and then the more often you recognize it, the less often you have to use the formal charge formula. But it's never a bad idea to also use the formal charge formula to just double check your calculations. So nitrogen is really common as well. Oxygen and nitrogen are the most common elements we see bonded to carbon, other than hydrogen, of course. So we want to be used to what's happening with nitrogen as well. So anytime I have a negative charge on a nitrogen, it's pretty much always going to be 2 lone pairs and 2 bonds, right? So just to show the formula there, nitrogen needs 5 electrons to be balanced. If it has 2, 4 all to itself, and half of 2, 4 that it's sharing, that gets me to 5 minus 6, or negative 1. It's not that stable. We don't really see that very often. There are instances where we will see that, but it won't be often because, as we said in the case of carbon, a negative formal charge on a really small atom creates a big imbalance between the positive and negative ratio. So for nitrogen having 7 protons, if it has an extra negative, it has the equivalent of 8 electrons around it. So if I do 8 divided by 7, I get 1.14. So it's got about 14% more negative than positive. It's not as bad as the almost 20% more negative than positive that the carbon had, but it's still more negative than positive, and it's still a significant chunk more, and that extra negative makes it unstable. The negatives repel. It has the potential to start sharing one of these pairs with another atom to balance its charge, and that makes it reactive. So what we pretty much see this doing in reactions is it will find anything like a hydrogen or something to start sharing this lone pair with to make a third bond and balance out its formal charge. Nitrogen with a positive formal charge, we see that fairly often. That happens fairly well. Nitrogen has a low enough, even though it's one of the highest electronegativity atoms, its electronegativity is lower than oxygen and fluorine. So since it's not one of the most electronegative atoms, it doesn't really pull electrons away from these other atoms so strongly that it starts to weaken the bonds and pull the bond away from the other atom. So if this is like a hydrogen here, the nitrogen will pull electrons away from the hydrogen and create a very polar bond. If it were oxygen or fluorine, it would pull them even more strongly and it would start to break this bond. But oxygen's pretty good, or nitrogen's pretty good at sharing electrons with these other atoms, even if it takes on 4 pairs and then takes on extra positive. Even though it attracts the electrons in, it still doesn't attract them so much that it breaks the bonds really, really easily. So that's a situation that you might see fairly often. So you want to get used to looking at nitrogen's formal charge when it has 4 bonds and 0 lone pairs. In that instance, if it has 0 lone pairs, it has 0 electrons assigned to it only, and it has 8 that it's sharing, so half of those 8 will count toward its charge, and that's how I get a +1 in the formula. Alright, so that leads us to the second quiz question, where we're looking at an example of this skill being applied, where if I show you the charge, you are meant to put in the lone pairs. So obviously, if we start from left to right here, this carbon here doesn't have a charge shown, so I know it has 3 hydrogens and it doesn't have any lone pairs. Right? A carbon with no charge shown has to have 4 bonds and no lone pairs, so we don't have to necessarily draw that in on every carbon. But as long as you've got a neutral carbon, you know it's got 4 bonds, and you know it never has any lone pairs unless it's negative, or unless it doesn't have 4 bonds, in which case there'd have to be the lone pair would have to be shown. I wouldn't be able to expect you to know that if there's nothing shown. So if a carbon doesn't have a lone pair shown, and it also doesn't have a formal charge shown, you can assume it has 4 single bonds. We just talked about oxygen on the last slide, so we know that oxygen needs to have 3 lone pairs and a bond to be negative. So any of these negatively charged oxygens, we can do that for, and we can use the formal charge formula to verify that. We just showed how, that is a mistake, ignore that right there. We just showed how oxygen, if it has 3 bonds and 1 lone pair, that will make it positive. So that lone pair belongs there. This nitrogen has a -2, so we didn't really look at a -2 on nitrogen. That's really pretty unstable. 2 negatives shown there. Really unstable because of the charge imbalance. But that could exist under the right conditions. So we want to know how many lone pairs to put around here. So let's look at that. So we know nitrogen normally has 5 electrons to be balanced in charge because it's in column 5A. So if it has a -2, how many electrons are actually assigned to it? Well, if electrons are negatively charged, it needs 2 more electrons. So this would tell us that we have 7 total electrons that have to be assigned to that nitrogen if it's going to have 2 negative charges more than what it would normally have when neutral. So to put 7 electrons around it, I would put 6 of them in the form of lone pairs, and then the one that it's assigned from the pair it's sharing with the carbon here would make the 7th, and that would give it 7 electrons assigned and a -2 overall charge. There shouldn't be any lone pairs on the boron. Just to take a look at that real quick. This boron has 2 bonds shown and 2 hydrogens attached. So 4 bonds around a boron. Unlike carbon, boron only needs 3 electrons to be assigned to it when neutral. So if it's got 4 bonds and we're subtracting half the 8 electrons in those bonds, that's what counts for the -1 charge. So if you see a negative on a boron, that's just a 4 bonded boron. Would there be any lone pairs on this carbon here? No, because a positive charge means it has 3 bonds. So you also would want to recognize there's only 1 hydrogen attached to this carbon, not 2, because then it wouldn't be charged if it had 4 single bonds. And then the element that sometimes students forget to analyze, I'm not sure why, is sulfur here. So let's take a look at that. In the case of the sulfur, it needs 6 electrons to be balanced in charge because it's in the same column as oxygen, column 6A. If it has a positive charge, how many are actually assigned? Well, it have to be 5. I have to subtract 5 from 6 to end up with a +1 charge. So I'm assigning 5 electrons here. Right now it's got 1 assigned from this bond, 1 from this bond, and 1 from this bond. And any pair is shared, only 1 electron is assigned to each atom. So that gives the sulfur 3. If it needs 5, then I need to put 1 lone pair on it, so it has 5 total electrons assigned to it to balance out, or to end up with a +1 formal charge. Any questions about anything on there? Alright, so it's also important to start getting used to looking at bond line structures in 3 dimensions. So we talked about how carbon, if it has an sp3 hybridization due to having 4 single bonds, 4 sigma bonds, that is going to create a tetrahedral geometry. And a tetrahedral geometry is one where all 4 bonds cannot be in the same plane. So if I'm trying to imagine the structure on a flat screen, like on my computer screen or on a piece of paper, it's very difficult because this thing is not, all 4 atoms that are attached to the carbon cannot all be in the same plane as the carbon or the screen or the paper. And so one thing we'll do to try to represent the 3-dimensionality of these structures on a 2-dimensional piece of paper is any line that's just a normal line, if I just draw a regular line, that implies that that is in the plane of the paper. So if this is bonded to a hydrogen, that's in the plane of the screen. In a tetrahedral atom, you can only have 2 bonds in the same plane at the same time. You can flip the structure over like a pancake or rotate it around in space. You can get different bonds in the same plane at the same time, but only 2 at a time. So if I've got 4 bonds to this carbon, maybe they're all bonded to hydrogen in each position. Only 2 of those can be in the same plane, and the angle should be around 109 since it's a tetrahedral shape. That means that the other 2 bonds, if I wanted to show them in space, one would be coming out at me, and that's represented with the solid wedge. So that's coming out of the screen towards you in 3 dimensions. And the other would be pointing away from you, and the dash wedge indicates that it's dashed because it's like behind the screen or behind the piece of paper. And when I assign you model kits, if I forget to do that this week in lab with you all, please remind me to do that because the model kits are really helpful viewing things in 3 dimensions. So typically when we're using a bond line representation, we like to extend the carbon chain so it's all in the same plane. And when you make your models, I recommend when you get your model kit, make these structures. When you make a model of this structure, you can kind of see how you can get all the carbons in the same plane. And if you attach a chlorine here and here, you can attach them such that one chlorine is pointing out of this plane at you and the other chlorine is pointing away behind the screen, or really behind the plane that these carbons create when they're all in the same plane. I could make this ring all in one plane if I attach something to it. And this carbon here, for example, you can't have more than 3 bonds all in the same plane, or it won't have a tetrahedral shape. And if it's sp3, because it's got 4 bonds, it should have a tetrahedral shape. And so I can put all the atoms of the ring in the same plane, even though that's not the most stable arrangement for the ring, which we'll talk about later. If I put all the carbon atoms in the ring all in the same plane, this oxygen, there's 2 ways it could be positioned. It could be positioned pointing out at me, or it could be positioned pointing away from me. And that's what the dashes here communicate. It's pointing away from you, and the solid wedge over here would communicate that this OH group is pointing out at you. Sometimes rings fuse together. This probably looks really weird to you. This is a situation where I've got 6 carbons in a ring, all in the same plane, right? Because each of these carbons is connected to the next with a regular, old-fashioned straight line. There's not colored in or dashed or anything. But then I've got this part here where it's all dark in color. It's all colored in. That implies it's coming out at me. So this position, at this position here, and at this position here, each of these carbons is bonded to another carbon coming out of the plane. It's in front of the plane of the ring. So if I make the 6 carbons in the ring all in one flat plane, this carbon is in front of that plane. And likewise, the bromine is in front of that plane, and this carbon here is behind that plane. Right? So get used to working with dashes and wedges. Get used to creating models and seeing where things are in space, so you can then eventually get to the point where when you see something like this flat, you can create a nice mental image of what the structure actually looks like in your mind without having to use a model. A model is really a great gateway from getting from the way things look on paper to creating mental images of how they really look in 3 dimensions, because you can't really represent a 3-dimensional structure in 2-dimensional paper. Talked about that. There's other ways to show 3-dimensional structures. This one is a Fisher projection. I hate these. We won't be using them. The reason I hate this is because you have a 3-dimensional structure, but for some reason Fisher decided he wanted to represent that 3-dimensional structure in the flattest way possible, which is completely against what I think makes sense, because what he's done here is to create angles that look like 90 degrees, angles that look like 180 degrees, and it makes the structure look more flat. And if it's not a flat structure, that only makes things more confusing and difficult to see 3-dimensionally. So we will be avoiding those pretty much entirely. Here's another way to show the ring, right? So comparatively over here, we had this ring. The carbons of the ring were in the plane of the screen, and the OH groups were pointing either out at me or back behind. Over here, I've got the opposite. I've got the OH and the hydrogens in the plane of the paper, and I've got the ring 3-dimensional. So these groups here, you could also show these with dashes to show that they're pointing away and that the solid part is pointing out at you. So it's like taking the structure on the previous slide, rotating it in space 90 degrees. So now instead of the ring being in the plane of the paper, it's now rotated, sticking out of the paper out at me. And then this is another way of showing this bicyclic structure. And so I've got these atoms here. Actually, let me label that right here. This is carbon 3 right here. 4, 5, and 6. So these carbons kind of create a roughly flat area, and then this carbon up here, which is bonded to both 3 and to 6, is above the plane of the rest of the carbons in the ring. So this is kind of like looking at this 3-dimensional structure on the side. These are really weird. Once you start working with these, I encourage you to bring your model kits to lab and maybe just come up to me and demonstrate to me that you're able to make a model of a structure like this, so that you're not incorrectly thinking about how these atoms are actually connected. I can check it over for you. Normally I would make one and then just demonstrate it during class. Alright, any questions about that? Okay, so then resonance is the next topic we're going to talk about here. Resonance is an extremely important topic in organic chemistry. It's hard to overstate how often resonance will be a factor when explaining phenomena, the outcomes of chemical reactions, the stability of some molecules versus others, the existence of some molecules versus others. And so we really want you to develop as thorough an understanding of resonance as possible now, because we'll be relying on that to understand and explain a variety of things later in the semester. So sometimes when you have a structure or molecule, a typical Lewis structure or even a bond-like structure cannot adequately represent what the true nature of this molecule. If a molecule is capable of resonance, when Lewis designed his Lewis structures, this was not on anyone's mind. It wasn't known to exist, and so he didn't develop a way to represent resonance with a Lewis structure. So we're going to talk about what is resonance, and we're going to talk about how to represent structures that have resonance, so we can keep track of what that is and how it affects the molecule. So what is resonance? Resonance is, in short, delocalization of electrons in extended molecular orbitals created from multiple p orbitals overlapping side by side. P orbitals overlapping side by side, that's like a pi bond. So when we're dealing with resonance, we're only dealing with pi electrons, not sigma electrons. So that's one really helpful thing, right? So sigma electrons are not ever going to be in resonance. It's only going to be pi electrons. So for example, if I have a structure like this, I'm just making something up. If all the bonds are sigma bonds, there's no double bonds, there's no lone pair that could be a pair of electrons in a p orbital or a pi electrons. If it's only single bonds, there can be no resonance. So when electrons are in p orbitals overlapping side by side, if I just look at a standard double bond between two carbons, well, what that is my two carbons have hydrogens. Those hydrogens and carbons are all in the same plane. The pi bond is created when the p orbitals above and below the plane overlap side by side. If you recall, that overlap creates a new molecular orbital where the electrons exist above and below the plane of the nuclei. So that's just a standard pi bond. So what resonance is an extension of that. In resonance, all we're doing is maybe adding another atom. So instead of having just two atoms overlapping their p orbitals side by side, now I've got 3 or 4. And when those orbitals start to overlap, the pi cloud, due to multiple p orbitals overlapping side by side, extends over multiple atoms. That's what we mean by delocalization. The electrons are not just in one molecular orbital between two atoms, they're able to exist in a molecular orbital extending over 3 or more atoms due to all 3 or more p orbitals overlapping side by side. And so what that means is our Lewis structure can't really represent that. because the Lewis structure allows us to put the electrons between two atoms, or in some instances, obviously, we could put them on a single atom as a lone pair, but there's no way, when we're drawing a Lewis structure, there's no way to account for electrons that exist over three or more atoms, because a bond can only exist between two atoms, and a lone pair can only exist on one atom. So as we go through this discussion, we're going to talk about how to represent electrons that can exist on more than one atom, and how to recognize when this is going to be occurring. So there are really two parts of this. One is recognizing when resonance occurs, misspelled occurs, O-C-C-U-R-S. And two is understanding what resonance is, or drawing a structure that illustrates the resonance, or that shows the resonance. So there are really two parts to that. We've got to start with part one and then work toward part two, right? So you got to look for the possibility of resonance first. So how do I know when resonance occurs? Well, there has to be p orbitals overlapping side by side. So in this structure here, we can recognize it. Right? If I just redraw here, I have a little bit more space. If I have carbons with a double bond, well, I know that the pi bond there forms when I've got p orbitals overlapping side by side. What is a carbocation? Well, we just talked about carbocations. We said a carbocation is when a carbon has three bonds and no lone pairs. Well, the three sigma bonds would give this a steric number of 3. It would make it sp2 hybridized to create the 3 sp2 orbitals needed for the sigma bonds to form. And that means since only 2 p orbitals were mixed in to make that hybridization, there's still an empty p orbital hybridized. And so a carbocation always has an empty p orbital. And that means if a carbocation is adjacent to a double bond, then its p orbital can overlap side by side with the double bond. So when you're looking for resonance, it's important to be able to analyze the steric number, the type of hybridization, so that you can tell if there's a p orbital on that carbon that can overlap with neighboring carbons' p orbitals, which is what's required for the electrons to be involved in resonance. So that's step one. Recognizing resonance is possible requires you to see p orbitals overlapping side by side. So then step two for this structure would be, how do I think about what this structure really looks like? And that involves taking the original structure, showing how the electrons could move around and be positioned differently. So in this particular case, this pair of electrons could move over here, because if it moved over here, then that carbon on the right hand side would no longer be positive. But if it moved over there away from this carbon would now only have 3 bonds, and it would be positive. So what we're going to do first is to think of all the different ways the electrons could move, and then average all of those together, because that average of all the individual ways we could imagine the electrons being distributed that are significant is going to give us the true structure of what the molecule actually looks like. So hopefully that will make more sense as we go through and look at examples. So here, as we just said, in this particular example, the simple situation, I've got 3 carbons. How many hydrogens do I have on each of them? I've got 2 here. So it has 4 bonds. I've got 1 here. So that has 4 bonds. And I've got 2 here. This carbon only has 3 bonds, right? We just talked about carbocations and how if the carbon only has 3 bonds and no lone pairs, that's what gives it a positive charge. Right? So here, this is a nice drawing that shows how all the carbon and hydrogen nuclei are in the same plane, and how the p orbitals extend above and below that plane and are able to overlap side by side. If they overlap at the same wave sign, they constructively interfere, and that will create a molecular orbital with lots of electron density in the area of overlap above and below the plane, so those electrons can attract to all these nuclei at once and extend over multiple atoms at the same time. And when that occurs and the orbital extends over multiple atoms, I can always still only have at most 2 electrons in a single orbital, but those electrons can exist all over that whole area of overlap at the same time, or all over the area of constructive interference at the same time. That's what resonance is. So in this structure I can recognize it's capable of resonance because of the overlapping p orbitals and the constructive interference that would result, that it would allow those electrons to exist in the extended molecular orbitals spread out over multiple atoms. So here's what my orbitals would look like. I've got 3 p orbitals overlapping, so I have to create 3 molecular orbitals. Right? We talked about molecular orbitals and how anytime atomic orbitals overlap, they disappear and create new molecular orbitals, and the number of atomic orbitals disappearing has to be equal to the number of molecular orbitals forming. Right? So in this case, on these 3 carbons, there are the sigma bonds, and I've got 1 p orbital, that's 1 orbital. I've got a second p orbital, that's 2, and I've got a third p orbital, that's 3. And when they're, if I drew them a little wider, you could see them overlapping. I've got 3 total p orbitals, and so I have to create 3 new molecular orbitals. If there's an odd number of molecular orbitals created, I can't have equal amounts of antibonding and bonding. And so then one of the orbitals will always be equivalent in energy to a non-bonding situation. But let's take a look at this. So here, the bonding molecular orbital results when all of the areas on top have the same wave sign, and all of the areas on the bottom have the same wave sign. So it's constructive interference all the way out around the top of the molecule and also on the bottom. That's the most stable orbital for the electrons. So if I only have 2 total electrons, they're going to both go into this orbital. This is 1 orbital, even though it has 2 sections, right? Because there's still a node in the plane of these carbons. So there won't be any electrons in the plane of the nuclei, just above and below that plane. But since there's no destructive interference, all of the area of overlap above and below is going to be high or rich in electron density. So I've got 2 electrons occupying that space. They can attract all 3 nuclei at once and spread out over the whole orbital. That's really stabilizing. In this case up here, the non-bonding situation, I see I have a node. And in the anti-bonding situation, I can see 2 nodes. So the more nodes there are between the nuclei, the less effective the electrons will be able to attract to the nuclei, because they attract better if they get in space between the nuclei above and below the plane to attract to those nuclei. So how many electrons do I have in this situation? I've got 3 orbitals. Ideally, I want only enough electrons to fill the bonding molecular orbital and none of the others. And that is the case, right? Because in this particular carbocation we're analyzing, there are a bunch of sigma electrons, but those are in the sigma bonds and the molecular orbitals that result from the head-on overlap. We're just looking at the pi electrons here. So how many pi electrons are in the carbocation? 0. There's 0 electrons in the p orbital. How many pi electrons are there here? 2. 2 pi electrons, because there's 2 electrons in the pi bond or in the space in those p orbitals. So if I only have 2 total electrons, they all go in the bonding molecular orbital and they're all stabilized over all 3 atoms. That's what resonance is. Resonance is a stabilizing force or stabilizing phenomena because it allows electrons to get into bonding molecular orbitals that are spread over more atoms than they would otherwise be spread over, and that allows the electrons to be extra stabilized because they can attract to all those nuclei at once. So we're talking about this carbocation here that has a +1 charge. So normally when we think of formal charge, we try to calculate formal charge for a specific atom. But in resonance, sometimes the formal charge is spread out over multiple atoms. And in this case, we can see that by looking at the resonance contributors, and we can also see it by looking at the molecular orbitals. Right, so let's talk about that. So as we said, if I think of the structure as being static or not in resonance, the positive is always on this one carbon. I could imagine, well, maybe these pi electrons move over here. And if they do, I'll create another structure. So one incorrect way to think about this is you don't want to say, well, sometimes the structure looks like this, sometimes the electrons move over and it looks like this. It's not a situation where the electrons are shifting back and forth, creating sometimes it looks like this and sometimes it looks like this. Because in reality, neither of these exist. What exists is the average of them or the hybrid of them. So we don't have electrons existing in one spot and then shifting over to the other spot. The electrons exist all over all three atoms at one time because they're in a molecular orbital that's spread over all three atoms at one time. So I've got 2 electrons in this orbital. I don't have any electrons in this orbital, which means the clouded areas here and here where the electrons would normally be are empty. And that means there's going to be the positive charge, it'll end up being a partial positive, is going to be spread out over both of these areas. So the molecular orbital that's empty, because there's not enough electrons to balance out the total charge, is showing me where that charge is going to be distributed. And likewise, if I look at the individual ways of showing the electrons and recognize that really neither of those exist, but what exists is the average, well, if I try to average these two structures together, what does it look like? Well, I don't have the pi electrons over here, and I also don't have them over there. I have them on average in both locations. So we use a dotted line to show the electrons spread out over all three of those atoms. And the positive charge isn't really over here on the left. It's also not really over here on the right. It's in the average of those two positions, which means half of it is spread out on the left and the other half is spread out on the right. Or partial charge, partial positive on the left, partial positive on the right. So hopefully both of these analyses help you to understand that the center carbon here is not going to carry the partial positive. The area that's missing electrons, that's making it positive, are the two areas on the left. That's where the cloud is that's empty, that is empty because there's not enough electrons, and not enough electrons means I've got a slight net positive on both those areas. And likewise, when you see the positive existing on either the left or the right and recognize that neither of those exist, but what exists is the average or hybrid of those, I have positive for the left and the right simultaneously in the true best representation of that structure. So when we're, just go back here for a minute. So when we're talking about these two steps, recognizing when resonance occurs, that was step 1. That's looking at to see if there are p orbitals that can overlap side by side. Step 2 is drawing a structure that shows the resonance. So in order to do step 2, I have to start by drawing each individual imaginary structure that doesn't really exist but does contribute to what the true structure looks like, and then imagine what the average of those is going to look like. We're going to do more of that on Thursday. So when we use the term contributor, the point of that term is to help you remember that these two structures don't exist. Okay, it's not like an equilibrium where half the molecules look like this and the other half look like this, or that's shifting back and forth. In reality, neither of these exist, but they do both contribute to what the real structure looks like. If I average these two together, I can draw the real structure where I can show the partial positive on both sides and the pi electrons not really being on the left or the right, but being spread out over both locations at the same time. And so These brackets are another way of just kind of showing neither of these structures exist, but since these are the best Lewis structures I can draw, and I can imagine the electron shifting from one position to the other, and then shifting back to the original position, it is helpful to draw them individually even though they don't exist, because once I have them drawn, then I can imagine what the true structure looks like, because it's always going to be the average of the individual structures that don't exist but do contribute to what the true structure looks like. And so there's the resonance hybrid for those two. How is a resonance arrow different from an equilibrium arrow? That's important. The resonance arrow is one single line with a head on either side. That arrow communicates that these structures don't exist, but they're contributing to what the true average structure looks like. An equilibrium arrow is two arrows pointing in opposite directions. That, hopefully you remember from Gen Chem 2, so we did a lot of equilibrium and nice tables and stuff there. That means that A converts to B, B converts back into A, and these two just keep shifting back and forth. Some of the molecules will look like this, some will look like this. That's different from resonance. None of the molecules look like either of these, but it's useful to draw them because they help us understand what the true structure looks like. And the analogy I think is quite apt is the analogy of a nectarine. If you don't know what a nectarine is, it's a fruit that was created by mixing the genes of a peach and a plum. Right? So a peach and plum are different things. A nectarine is not a fruit that sometimes is a peach and sometimes is a plum and shifts back and forth between those two identities. It's always the average of the two, just like in resonance, the real structure is the only one that exists and is the average of the two. It's not like it's multiple things shifting back and forth. So how is resonance stabilizing to a structure? These 2 points are really important, so you should definitely know them, which is why I wrote them out here in explicit detail. So as we said, the true structure is more stable than any one of the individual contributors, and that's one, because the electrons are delocalized, meaning the electrons are spread out in a molecular orbital tract into 3 nuclei at once and minimizing their repulsions with one another, versus being in a small orbital that would be spread out over only 2 atoms at a time, where the electrons would be closer together repelling. So the delocalization of the electrons is a key thing. That is always present in resonance, and it's always stabilizing. Delocalization of charge usually occurs, but not always. So in this case, I have a charge. If the charge existed on a single carbon, that carbon would be unstable because of the big charge imbalance. So it's less stable than it would be if the charge is instantaneously spread out over multiple atoms, because then each individual atom only carries a partial charge, which isn't as bad or isn't as stable. So spreading out the charge when it occurs is also stabilizing for the structure versus having all the charge concentrated in one spot. And we know partial charges are not nearly as destabilizing to a structure as full formal charges. Alright, so we want to be able to look at more complicated examples. Right? This example we've been looking at so far is very straightforward. It's just a situation where you've got a few carbons and a pair of electrons. You've got p orbitals on all 3 atoms overlapping side by side, which allows the electrons to shift around. Really, they're not technically shifting around. We're just showing them existing in multiple locations so we can recognize what the true or hybrid structure actually looks like. But as you probably recognized in that 3rd quiz question, these molecules can get very complicated, and so you want to practice and develop the skill where you can show all the contributors so that you can get a sense for what the average of all these multiple contributors might look like. So in this case, there are only 2 contributors, and the average of them is pretty easy to show, where the electrons exist over all 3 atoms at once, and there's a partial positive on either side because that one positive is spread out over both atoms. If I've got lots and lots of atoms and lots of electrons that can possibly shift around, we want to help you with some guidelines and rules so you're showing the shifting happening in reasonable ways that leads to structures that you can then average together to get the hybrid, which is what we'll be talking about mostly on Thursday. So there's these curved arrows. The curved arrows show electron movement, right? So that's what this curved arrow here was showing. Right? If I draw the best Lewis structure I can for this molecule, and then realize, well, there's going to be a possibility of electron pair to shift over here and exist on the other side, the curved arrows are a way of helping me work through every possible distribution of the electrons that would yield every possible contributor that I can then average together to get the overall molecule. So the rules for curved arrows, and these are also going to be used later in the semester, and this is the whole point of you downloading and working in the Mechanisms app, is to get used to working with these curved arrows. The curved arrows are really not intuitive for students in general. They're complicated and not easy to master, and they take a ton of practice. So in addition to the Mechanisms app, please work through the examples in the end of the chapter and let me know if you need help with those, because the curved arrows are a challenge. They're not easy. We got to follow the rules. So the curved arrows show electron pairs moving. They show electrons moving. So the arrow must start where there are electrons. The arrow does not show what has already happened. The arrows show what is about to happen. So we always start with our structure, and then we draw the arrow to show how that structure is going to change into the new structure. The arrow starts on a pair of electrons, and it points to the location where the electrons will end up. So this arrow here is showing these electrons moving over to here. I'm not going to show them over there in the original structure. If I draw them in here, that looks bad, because now it looks like I've got them here and over here at the same time, which actually is kind of what's happening in the hybrid, but I don't want to show that until I show the hybrid. And when I do in the hybrid, there'll be dotted lines to communicate that. So for now, I'm using the arrow to help guide me toward what the next structure is going to look like. It's also giving us practice with the arrows. It's going to be relevant throughout both the end of this semester and next semester. So let's look at the rules for curved arrows. Guidelines for curved arrows. 1. And these are only the rules specifically right now. We're just talking about the resonance. So even though there are many instances where sigma bond or single bond electrons will shift around, that's not going to be happening in resonance. So we want to avoid breaking or forming or involving in movement any sigma electrons or single bond electrons. So only the pi electrons are moving in resonance. Lone pairs can be in p orbitals and can count as pi electrons, or double or triple bonds. So that's pretty much it. In resonance, it's always going to be double bonds, triple bonds, or lone pairs that are moving. So rule 2, and this is a rule for always, not just for resonance. Never exceed 8 electrons around a second energy level atom. Right? So this is a bad arrow. Moving these electrons in here would create a double bond, and that would mean too many electrons around this carbon. So any carbon that's got 4 single bonds, it doesn't have a p orbital. It's already mixed its p orbital in with the s to make sp3 orbitals. And if there's no p orbital, there's no p orbital overlap, there's no resonance, so I can't move electrons in there, and I definitely can't expand the octet for a second energy level atom beyond 8 electrons. So for carbon, for nitrogen, for oxygen, these are all bad because I can't move the electrons in there and make a double bond. What this arrow would normally be communicating is that the lone pair, where it is now, is going to move in here and create a double bond. And that's a bad arrow because obviously when it does, when I follow the arrow, I create too many electrons around an oxygen. So how does this one look? Well, it might not look as bad to you, but it should. And hopefully if you start to get into the habit of, at least for now, drawing in the hydrogens around the relevant area of electron movement, you'll see that, because this carbon here already has 4 bonds. I can't move another pair in and make a double bond to it. That would make a 5 bonded carbon, which is not possible and it's prohibitively unstable. So I don't want to show that arrow, and I don't want to think about moving electrons into that spot. So avoid breaking single bonds, and make sure you don't create any 5-bonded atoms or atoms with more than 8 valence electrons if they are second energy level atoms. Third and fourth energy level atoms can hold more than 8 electrons, so it's okay to do that for them. All right, so that's rule 2. Rule 3. Sometimes, but not very often, second energy level atoms may end up with less than 8 valence electrons. So this can happen. It's not very stabilizing, but it is significant. So this is legit. This is a good arrow. This arrow shows the pi electrons moving up to the oxygen. The arrow shows the electrons that were being shared between 2 atoms, which is why the arrow is starting there. It's this pair of electrons, and the arrow showing it where those electrons end up, which is as a lone pair on the oxygen. That creates some formal charges. So this is kind of unstable. But it is significant. This is a minor contributor. Not all contributors contribute the same. And that's where the nectarine analogy is even more apt. Because a nectarine, if you taste one, it tastes more like a peach than it tastes like a plum. It has more peach characteristics than it has plum characteristics. It's still a hybrid of both, but the peach factors in to a greater extent than the plum does. So if I'm looking at the hybrid or average of these two structures, well, the average will look like this. Right? So the electrons that are in resonance, I show with a dotted line. And the electrons that are not moving, which would be this lone pair and this lone pair, are still shown there. So the dotted line helps me to recognize that these electrons are in resonance. But I also always want to look for charges on my resonance hybrid. Right? So because this carbon in one structure has 0 charge, and in the other structure it has a plus charge, that means it will have a very slight plus. We already knew it had a plus because of the electronegativity difference pulling electrons up. But it has a greater partial positive here than would only be predicted by the electronegativity difference and the electron shifting away from that carbon, which means that the resonance is significant. It is creating an additional quantity, some quantity of partial positive on that carbon because of the fact that this contributor is factoring in to the average or real true hybrid structure that exists. And when the electrons shift up here and creates a negative on the oxygen, the average amount of charge on the oxygen that would exist on the true hybrid structure would only be a partial negative. So we can see how the resonance contributes to there being extra amounts of charge on the carbon and the oxygen, and that makes the carbon even more attractive to anything that might be negative that could come in there and form some kind of attraction. So this resonance hybrid shows how the charges are distributed due to the resonance, and the pi electrons being in resonance is demonstrated or shown with the dotted line there. So if I have a minor contributor and a major contributor, the true structure is going to look more like the major contributor, right? So I don't have a ton of partial charge there, but it has a little bit due to the slight influence of the minor contributor on the overall average structure.
I have a question.
Sure.
So in this specific example, in the resonance hybrid, we represent partial charges rather than formal charges because only the minor one had formal charges?
Correct. Right.
Okay.
So in the hybrid, for any atom, you want to look at every instance where that atom occurs in each contributor and look at the charges it carries in each contributor. So in this contributor, it's neutral. In this contributor, the oxygen carries a negative. So what's the average between 0 and -1? Well, something in between 0 and -1 would then obviously be a partial negative or a fraction of a negative. So, I mean, I wouldn't expect you to calculate the exact fraction, right? Because there's no way at this point to quantify how much the minor contributor contributes to the average versus how much the major contributor contributes to the average. But we could say that the quantity of negative here is probably going to be less than 1/2, because 1/2 would be directly between 0 and -1. And if the charge were exactly 1/2, that would imply that the two contributors are equally contributing to what the average or hybrid looks like. So since the major contributor contributes more, we can predict a small partial negative here, because for the most part that oxygen is neutral, and only the negative only factors in a little bit.
Thank you.
You're welcome. All right, so when you're using curved arrows in resonance, make sure you show any formal charge that exists in any contributor that you would create. Right, so we'll take a look at these electrons here, and the arrows. What are the arrows showing? Right, so this arrow is showing this pair of electrons moving in to form a double bond here. I don't want to show it yet. Right, the arrows are showing what's going to happen, not what's already happened. So I want to draw the second structure over here. So to do that, I would then, if the arrow is showing the electrons moving in, I would put them in there. This lone pair has no arrow on it, so it's still there. I've got two arrows here. Why do I need two arrows? Well, if this pair of electrons were still there, well, then I'd have a 5-bonded carbon. So I can't do that. So in this case, the resonance requires two arrows to show the electron movement, not just one. So if I get two arrows shown at once, that means I've got to move both pairs of electrons at the same time. So this lone pair moves in to form a double bond here. This double bond moves out to become a lone pair. Right? That's important. The arrows show where the electron starts and where it ends. So this arrow here is different from this arrow here. They're both starting in the same place, so they both would indicate the movement of the pi electrons. But one arrow would show the electrons existing then as a lone pair, versus the other arrow would show the electrons existing as a double bond. And electrons can shift from a space between two atoms to one of the atoms as a lone pair, or between the next two neighboring atoms in the next space. So why is that unreasonable? If I could draw that structure. Why is this here an unreasonable structure? It looks fine to me. The problem is it can't form from the original structure, because in the original structure I have an sp3 hybridized carbon on the end that has 4 bonds already. And if I move more electrons toward it, well, now it's going to have 5 bonds. I can't do that. That's not possible. So my arrows have to be very precise. They have to move exactly to the space between two atoms, or to an atom, to indicate their new location in the new structure. And then I need to analyze the formal charges of those atoms. So like we talked about at the beginning today, I'll look at the formal charges. Now I've got formal charge positive on the oxygen, negative on the carbon. And so if I were to show the resonance hybrid there, it would be the average of this structure and this structure, structure 1 and structure 2. The individual contributors don't exist. What exists is the average. And so to draw the average, and we'll talk more about drawing hybrid averages next time. Any electron that's involved in movement, I show that with a dotted line. Right? This lone pair is not moving, so it's still there. This pi electron is also moving, so I would show a dotted line there. And now I have a partial positive on the oxygen and a partial negative on the carbon. Why partial? Well, again, I'm averaging the charge existing on this contributor with the charge existing on the other contributor. The oxygen's real charge is somewhere between 0 and +1, which is a partial positive. And the carbon's real charge is somewhere between 0 and -1, which is a partial negative. So I also want to make sure my arrows don't violate any of the rules. So have these arrows violated any rules? No. I can move the electrons in here. I'm only moving pi electrons, so either lone pairs or pi electrons. I'm not breaking or forming any sigma bonds. I'm not breaking or forming any, I'm not breaking any octets or expanding any octets beyond 8 atoms. So this is a reasonable contributor. This is a reasonable contributor. They both contribute to what the average or hybrid structure looks like. Every resonance contributor that you draw should be, you should be able to draw the electrons going back to the original position. So just to show how that would work with the arrows, if I want these electrons to move back, I want to move this pair from being positioned as a lone pair to being positioned as a pi. So I always start the arrow on the electrons. I guarantee many of you are going to start drawing arrows starting from atoms. Don't ever start an arrow on an atom. It always starts on electrons. It shows electron movement. So I start the arrow on the electrons. Oops. Start the arrow on the electrons and the arrow either in the space between two atoms where the electrons end up, or on a specific atom if they end up as a lone pair. In this case, they're ending up as a pi bond between atoms, so my arrow points to the space between those atoms. That can't be the only arrow, though, because that would make a 5-bonded carbon. So at the same time, I've got to move these pi electrons back up onto the oxygen. And when they move back up to the oxygen, this arrow is indicating which pair of electrons is moving and which atom they're moving to, indicating that they're going to exist on that atom now as a lone pair. You can think of the arrows as indicating the direction that the charge will flow. That's not really what resonance is, right? So if we really want to imagine what resonance is, it involves p orbitals overlapping side by side on each of these atoms, and it creates molecular orbitals extending over all three, and the electrons are spread out over all three of those atoms simultaneously. Alright, so to also help you, so we just kind of talked about what not to do with arrows. Here are some common ways that the arrows will move. So this should be pretty comprehensive, and again, this is only for resonance. So there are going to be more patterns than just these for electron movement, and we start to see other reactions. But when we're just talking about resonance, these are the main, these are the ones. These are the 5. So let's look through these one by one. So the first one is an allylic lone pair. Well, what the hell does allylic mean? Allylic is a term you're probably not familiar with, so we've got to define that. So a couple new terms here. Vinyl and allyl, or vinylic and allylic. These refer to proximity of an atom or a pair of electrons from a double bond. So vinyl lone pair, for example, is going to be one that's directly on an atom that's involved in a double bond. An allylic lone pair is going to be one atom away from an atom that's directly involved in a double bond. So here are my vinylic sites. Those are the ones directly involved in the double bond. Right? So if I had a vinylic lone pair, it would be directly on that. Allylic positions are one more atom away. So an allylic lone pair would be not directly on the atom involved in the double bond, but one more atom away. Why is that important for resonance? Well, let's look at the orbitals that are involved. If it's a vinylic lone pair and it's already on that atom, well, the pi electrons for that atom are already occupying its p orbital, which means the lone pair is going to be in an sp2 orbital. sp2 electrons can't be involved in resonance. They have to be in a p orbital. So that's why I want to look at allylic electron pairs. Those get involved in resonance because an allylic lone pair can exist in a p orbital. Let me draw it down here. Dang it, I'll draw it over here. The lone pair, if it gets in a p orbital, then that can overlap side by side with the p orbitals that make the double bond, and that allows for resonance. So allylic lone pairs are good in resonance, and we can show with an arrow them moving in here and pushing these away. Vinylic lone pairs cannot be involved in resonance because they're not in a p orbital that would overlap side by side with other p orbitals. And so make sure you can identify allylic versus vinylic lone pairs, as well as allylic versus vinylic chlorides or other atoms that might be attached to a chain. Right, so the vinylic ones, I'll put a V next to those. This is a vinylic chloride, and this is a vinylic chloride, because the chloride is directly attached to an atom involved in the double bond. Same thing here. It's directly attached to an atom involved in the double bond. Right? If I had a lone pair here instead, that'd be a vinylic lone pair, because it would be right on the atom involved in the double bond, and the chlorine is on the same atom, so the chlorine is vinylic. My allylic chlorides are this one, and this one, and this one is neither, because it's not close enough to the double bond. It's too many atoms away. So the allylic one is not directly attached to the double bond, it's one more atom away. And this one here, it's not directly attached to the atom involved in the double bond, but it's one atom away from the one involved in the double bond. So hopefully that helps you with those new terms. And now we can start to talk about resonance. So the first pattern of resonance are allylic lone pairs. My allylic lone pairs, as we just said, can exist in a p orbital. And that's contrary to what we talked about earlier in the semester. Early in the semester we said if an atom, like a nitrogen or a carbon or whatever, has 3 single bonds, like these ones do, and a lone pair, we normally would count that. The steric number would be 4, because the steric number is the total of the number of lone pairs and the number of sigma bonds. And if it was 4, it should be sp3. It should not have an unhybridized p orbital to even allow for resonance. But because resonance is stabilizing, that means that this lone pair is actually more stable in a p orbital. And so this, we would normally predict this as being trigonal pyramidal. We would predict the lone pair would push these down and would make a pyramid shape. And that's usually the case for a lone pair on a nitrogen. But if the lone pair is allylic, it's an exception to that situation. Because an allylic lone pair creates a different geometry. Instead of being a trigonal pyramidal and existing in an sp3 orbital, even though the steric number is 4, we have to recognize this is a special situation where the lone pair, if it gets in a p orbital and the nitrogen ends up sp2 hybridized instead of sp3, then that p orbital can overlap side by side with the p orbitals involved in this pi bond, and that can allow for resonance, which stabilizes the structure and allows the pair of electrons in the p orbital to be more stable than they would be in an sp3 if it were to hybridize in the standard way. So my allylic lone pair can be involved in resonance. It can move in here. That would create a 5-bonded carbon, though, so I'd have to also move these onto the next carbon over. So when we're doing allylic lone pairs, we're always going to have 2 arrows. So first you've got to identify the allylic lone pair. This is an allylic lone pair. Either one of these could count as an allylic lone pair. This is an allylic lone pair. It's one atom away from one that's directly involved in a double bond. Same thing here. Same thing here. Anytime I have an allylic lone pair, I need 2 arrows to show how to get to the next resonance contributor. 1, 2. 1, 2. 1, 2. These can move in here, push these out here. If I only move 1 arrow, it creates a 5-bonded atom, so I got to move another pair of electrons away. So when we're doing that, we want to be able to draw the resulting structure. Right, if these move in, forms a double bond. These move out, forms a lone pair. So I've got 2 resonance contributors that would each contribute to the real structure, which would be the hybrid. Same thing here. Move this pair in, move this pair out, redraw it, following what the arrows are showing. Now, this one in particular creates some unstable formal charges. So if I've got 2 contributors, and one is neutral and the other has unnecessarily unstable formal charges, well, the real structure is going to look more like the neutral one than like the one with charges. But in reality, the hybrid would have some characteristics of both. Same thing here. You can move the allylic lone pair in, push the pi electrons away. Oops, should be oxygen there. This one also creates some unnecessary formal charges. So again, the hybrid would look more like the neutral structure than it would look like the one with the charges. Here I've already got a charge on my allylic lone pair, so if I move it in and push the other electrons away, all it does is simply move that negative to another atom. So here, the resonance, average or hybrid, would look a lot like both because the two individual contributors are pretty similar in stability. They're not the same in stability. Nitrogen has one proton more than carbon. So the nitrogen can stabilize the negative a little bit better than the carbon can, which means this would be the major contributor, and the average or hybrid would have a little bit more negative on the nitrogen than it would have on the carbon. And then the last structure here, my allylic lone pair moving in, pushing electrons up. Again, in this case, it creates a couple charges that didn't already exist. And so the average structure is going to look a lot more like the neutral one than the charged one. So practice with that particular pattern. The next pattern is an allylic carbocation, or an allylic positive charge. It doesn't have to be on a carbon, but a positive charge. We saw this one already. This one involves only one arrow needed because the neighboring atom doesn't yet have a noble gas configuration. So all I have to do is shift one pair of electrons over to complete it, but in the process, it leaves the other side without a noble gas configuration. So normally that's really unstable, but the fact that that resonance stabilizes the structure is in large part what allows it to form or exist. There could be multiple instances of one arrow shifting electrons. So in this case, I've got a positive charge here, so sometimes students get confused about what direction to shift the electrons in, right? You definitely do not want to shift the electrons in this direction. There's two reasons for that. One, well, there's a positive over here, and the positives attract electrons toward it, not away. And two, even more importantly, this carbon already has 4 bonds, so it's a good idea to get used to drawing the hydrogens in. If you can recognize something already has 4 bonds, hopefully that will prompt you to realize don't push electrons over there and make a 5th bond. So don't do that. We want to move the electrons toward the positive charge. I'm not showing the electrons move all the way to the atom. They're not going over there as a lone pair. I'm shifting them into the space to satisfy the noble gas configuration of that carbon. That does pull them away from this carbon. So now there's a positive here. And then more electrons can shift again. And I can create a third structure. So in the quiz question today, hopefully most of you realize there's multiple structures that can exist because if there's multiple pairs of electrons that can move, each pair moving creates a new structure that would then contribute to the hybrid or average. So if I'm drawing the average for this one, I've got 2 pairs of electrons total that can move. And all of the areas that those electrons are spread out over would involve a dotted line. Oops. The end carbon is not involved. At no point do electrons exist on it. Pi electrons. So I don't extend my dotted line to include any atoms that aren't actually involved in sharing any of the pi electrons. So I need my dotted line to cover the atoms that share the pi electrons, and then I need to show where my charge exists. I've got one positive charge on the structure spread out. Well, I've got 6 carbons. That one positive isn't spread out over all 6. I could only draw 3 contributors. So that one carbon is spread out over carbon 1, carbon 3, and carbon 5. And so those are the carbons that carry the partial charge specifically in my hybrid structure. The third pattern is pretty straightforward. This is the pattern where you have a lone pair adjacent to a positive charge. And so if the positive charge is on an atom that does not yet have as many electrons as it could hold, all you have to do is shift a pair of electrons in there. So again, this is another case where I have only one arrow. All I have to do is shift those electrons in, and that alleviates that positive charge because now there are 4 bonds. So I can do the same thing here. When I move the electrons in here, I'll form a positive on the oxygen. So in this case, this structure is more stable than this one because it has complete noble gas configurations for all the atoms, whereas over here, this carbon doesn't have a complete noble gas configuration. So that's why this is the major contributor. But the average or hybrid would look like both. If I wanted to draw the average or hybrid there, I would have the pi electrons represented with the dotted line, and I would have a little bit of a partial charge on both those atoms because they're sharing that one formal charge simultaneously in the resonance hybrid. We can look at the same type of movement in a nitro group. Here I've got a lone pair adjacent to a positive charge, so I can imagine shifting this lone pair in here. Does anyone see a problem with that? Yeah, I've got a problem. So what's the problem with that? Well, the problem is if I move those in, I create a 5-bonded nitrogen, which is impossible, just like a 5-bonded carbon is impossible. So here, sometimes if you're moving a lone pair in toward a positive charge, you may need a second arrow to avoid a 5-bonded atom that can't have 5 bonds. So if I'm going to do that, I have to also move this pair out. So doing that, I can see the resonance that occurs for this nitro group, where no matter how I draw the resonance structure, there's always a positive formal charge on the nitrogen, but the negative formal charge is spread out over the oxygen on the right as well as the oxygen on the left at the same time. So if I were to look at the hybrid here, I could show the pi electrons moving with the dotted line because they're shifting. It looks like they're shifting back and forth, but in reality they're spread out over all those atoms at once. We've got 2 lone pairs on each oxygen that don't move or are not delocalized. I've got a full formal on the nitrogen that doesn't change. And I've got the formal negative spread out equally over those 2 oxygens because they're equivalent. So 1 negative charge spread out over both oxygen atoms. The fourth type of electron movement or pattern is where I've got pi electrons shared between 2 elements with different electronegativities. I want to remember that the more electronegative an atom is, the more effectively it attracts electrons. So if that's
really quick.
Yes.
What was the charge that was spread out between the oxygens?
Yeah.
Okay.
This -1 charge here. So in any one contributor, there's a negative formal charge for one of the 2 oxygens. And this contributor exists on the oxygen on the right. Here it exists on the oxygen on the left. So since it really exists over both simultaneously, they both at the same time carry half the negative. Yeah, so over here we're saying here the carbon and oxygen have different electronegativities. So the electrons have to shift away from the carbon toward the more electronegative oxygen. That creates a minor contributor. So this is significant, as we were saying earlier, because it does create some measurable amounts of charge that wouldn't normally exist, but it's minor because these charges are definitely way less stable than the neutral structure. So we want to keep in mind that that's significant, but it's not a major thing. And we could do the same thing here, shift these electrons out here. Here it would be even less significant because it can create a contributor with a much less stable negative charge. Yeah, I saw the unstable positive charge there. So these electrons would be likely to shift back in and go back to the original structure. And in reality, as we've been saying, none of the contributors actually exist. What exists is the average of them. But when one is way more stable than the other, the average is going to look a lot more like that one than the less stable one. And the last one is when you have conjugated pi bonds in a ring. Conjugated means you're alternating double, single, etc. around the ring. And so I've got a double bond, single bond, double bond, single bond, double bond, single bond, all the way around the ring. As long as it alternates double, single all the way around, then the electrons can be shifting around. We can show the arrows moving the electrons around counterclockwise, or we could also show them moving clockwise. So the clockwise direction, shifting around one bond at a time, right? So in this case, I don't have to move the electrons onto an atom as a lone pair. I'm just shifting them into the next space, and as long as I do that with all three pairs at once, then I can create the other structure, and I don't break any noble gas configurations or create any unstable formal charges. So what type of motion do the electrons actually have? It kind of makes it look like they're in one position and then they shift and then they're in the next position. Got to remember, it's not shifting back and forth. The reality of the situation is the hybrid. And in the hybrid, the electrons are all over that area at once. There's a molecular orbital that spreads out over all 6 atoms, and those electrons exist in those molecular orbitals that extend over all 6 atoms, attracting all the nuclei at once. In this case, there are 6 pi electrons involved, right? 2, 4, 6. So I need 3 molecular orbitals to accommodate all 6 of those. I can only have 2 in an orbital at a time. So I mean, that's more of a OChem 2 topic to get into what those orbitals look like. But there are going to be molecular orbitals extending over all those atoms. And there are going to be 3 of them that are occupied by the 6 electrons that extend over those 3 atoms, or all of those 6 atoms. So this table summarizes those 5. And like I said, the more practice you get with these, the more solid your skills will be, the better off you'll be moving forward, and we'll be dealing with resonance a lot for the next year if you're in both semesters. So you want to make that a solid foundation as early as possible. So let's look at this example, and then we'll do the quiz example. If you have to go, I'll be recording this. You can always check back to the video on Canvas that I'll upload a little later. But we see a couple patterns here. So if your molecule has a couple patterns of these patterns, there's going to be multiple contributors that you'll have to draw. Right, so what's this pattern here? Here I have a lone pair adjacent to a positive charge. So that's a one single electron movement pattern. So once I look at that, I want to redraw this. I want to redraw the whole structure, leaving everything else the same, because I want to come up with as many reasonable structures as I can. So now my positive exists on the nitrogen. So what that shows me then is in this area of the molecule there's resonance, and the positive is instantaneously spread out between the nitrogen and the carbon. Is there resonance down here? Yes. I can also show, so before I talk about that, is it more stable to have the positive on the carbon or the nitrogen? As we were saying before, if a carbon has a positive, it only has 3 bonds. It doesn't have a noble gas configuration, so that's not very stable. So here, at least all my atoms have a noble gas configuration. So this is more stable. So since this one's more stable, I'm going to work from this to try to find the major contributor. So here, another pattern is the pi electrons shared between 2 atoms of different electronegativity. Nitrogen's more electronegative than carbon, so I could shift these electrons up. That would create another contributor. So I'm going to leave everything else the same. But I'm going to shift these electrons up to that nitrogen, and they're going to exist as a lone pair. Well, that creates some unnecessary formal charges. So this is not a major contributor. It's got lots of formal charges, making it unstable. But it's significant because it does help me recognize this carbon here is going to have a little extra positive, and this nitrogen is going to be a little negative, and that could affect the reactivity of the structure. Where else is there resonance? Well, I've also got some over here, right? So I can see here the pattern is I've got an allylic lone pair. This pair of electrons on the oxygen is allylic to this double bond, just like up here. So I can move this pair in here, I can't leave it there and only do that because I'll make a 5-bonded carbon, so at the same time I have to move these out. Where can I move them? Well, I can move them onto this carbon. So for the time being, since I don't have much space, I'm going to erase this structure. It wasn't very stable, so it would have been a minor contributor anyway, but if I'm looking for all the contributors, it'd still be important to draw that one. So if I'm moving the electrons in here, I'm keeping everything else the same. Keep this double bond here since that was more major than moving the electrons out and creating an extra formal charge. So if this oxygen moves the electrons in and pushes this pi electron pair out here, I'll have a negative charge here, and I'll form a double bond here. So that looks pretty good. I'm not quite done, because what that does is it opens up the opportunity for me to see another pattern, and it's right here. I've got a lone pair allylic to a double bond. I didn't really draw this too well. Try to make that a little sharper. So that means one more pattern where the electrons can move into the space between the atoms and push these onto the nitrogen. And that's going to create my most major contributor because it's going to have the least amount of formal charge. So I'll try to draw that one here. So when these electrons move onto the nitrogen, it's going to have a lone pair. This nitrogen still has a lone pair and a double bond. This lone pair moved in here to make this double bond. And there's my other resonance contributor. This is the most major one. It doesn't have any formal charge. But the other ones are important because they help me to see which atoms will carry partial charges in the average or hybrid that forms. Notice that areas where I've got sp3 hybridized carbons separate areas of resonance from other areas. So here, anytime I've got a 4-bonded carbon, resonance can never extend over that atom. So that's also another reason why it's helpful to draw the hydrogens in on atoms where that's the case. So that was a pretty complicated example, and so is the example, the last quiz question. So we'll just finish this off here. Even though we went over time a little bit, just want to explain it. So we showed where the lone pairs were on this one earlier. So let's draw those in so we can get started. Alright, so what are some of the patterns that we recognize, of the 5 patterns we saw? Well, looking over here, I see one. I've got a lone pair adjacent to a positive charge. So one thing I can do is just shift these electrons in here. So normally I'd redraw the whole structure, but just to save a little time, I'm just going to redraw this area of the structure. So I'm moving those electrons in. We create a double bond there. And then obviously the rest of the structure would be there. That alleviates the formal charge in that area. But it does cause the sulfur to have more than 8 electrons. Is that okay? Well, yeah, because we said only the second energy level atoms can never have more than 8. Third energy level atoms can have more than 8. So that is a significant resonance situation that would be occurring only on that part of the molecule. And because over here I have an sp3 hybridized carbon, none of that resonance can extend anywhere else. If there's resonance somewhere else, it has to be self-contained, separate from the electron movement that's occurring between the sulfur and the oxygen. So there's one pattern. What else can we see here? Well, right here, I've got a pi electron, a double bond, and I have a carbocation allylic to it. So this is an allylic carbocation. So I know that I can just move these electrons down there and attract that positive because that carbon doesn't have a noble gas configuration yet. So if I do that, if I just focus in on that part of the molecule, this double bond would be now down there. if this double bond exists here now, there's still a bond here to the sulfur, and the rest of the things are still attached to the sulfur. I'm just saving time not drawing them. There's still one hydrogen here, which could be helpful to draw in to see that now this carbon has a complete noble gas configuration where it didn't before when it was a carbocation. When these electrons move down, the carbon that's here is still bonded to the oxygen. And now when these electrons move down, now this carbon, which only has one hydrogen, because it can never have more than 4 bonds, becomes a carbocation because now it only has 3 bonds. And that creates another situation, another one of the patterns. So obviously the boron is still here, but we won't draw that in for now. We'll analyze that part in a second. So now the carbocation is adjacent to an atom with a lone pair. So that's another pattern. So this pair can also move in there. And that creates another structure. We're now forming a CO double bond. And now I don't have any formal charge on that area. So there's a fair amount of resonance right up in this area, as well as between the sulfur and the oxygen. So then let's look over here. Well, take a look at the boron. The boron is sp3 hybridized. It has 4 sigma bonds and no lone pairs, so it's a resonance blocker. Resonance cannot extend through there. So any resonance we've already talked about on the left-hand side is self-contained. Any resonance that can occur over here, it will be separate from what's happening over there. But it will still contribute to what the average or hybrid structure looks like. So let's take a look at that area of the structure real quick. So the boron has 4 bonds. This oxygen has 1 lone pair and a double bond. And then there's a carbon bonded to a nitrogen with a couple lone pairs, 3 of them. So that creates some charge. So that's pretty unstable. And so we'll look at our patterns and try to recognize one here. Here we've got this nitrogen's lone pair allylic to this double bond. So I want to move these in, but I have to do more than that, because since there's still a hydrogen here, I'd make a 5 bonded carbon if I only move more electrons in. So I have to move these out at the same time. So the resonance that's going to be created on that part of the molecule is going to alleviate the charge on the oxygen by moving these pi electrons to create a lone pair there. And it's going to create a double bond here. So I still have only a 4 bonded carbon, but now I only have a -1 on the nitrogen instead of a -2 when I calculate its formal charge. Any questions about any of that? Alright, well, there's a lot of bullet points associated with that, so there's plenty of practice for you to do to test yourself on that stuff. And you can always set up a time to meet with me virtually or talk to me in lab about any of the questions you have. On Thursday, we're going to continue talking about resonance, and then we're going to get into Chapter 3 about acids and bases a little bit. So most of that should hopefully be familiar to you from Gen Chem 2, where we talk about acid bases a lot. But we're going to review some of that stuff and talk about it in the context of molecules that involve carbon. And so make sure you do the Day 5 quiz by Thursday at 1. If anyone has any questions, I'm going to stick around here for a minute. If there's anyone left on the feed after going over by so much time.